Welcome back to neural nets learning, and we are talking about a single perceptron or a single neuron model. Okay. All right. Now what we would like to see now, how this perceptron model is able to learn a decision boundary given the data points. I mean, so for a simple test, I mean, without even using perceptron, just to see that if so something like this, I have a linear separating boundary, and let's say I have two classes C1 and C2. Okay, so let's say for a moment that this equation of this line is x plus 2y equal to 4. Okay, and if I ask the question, like I give you a bunch of points, and can you tell me whether these points lie on the line, whether these points lie on different sides of the line, and so on and so forth, right? When I give you these points, like let's say for example 0, 1 or 1, 0, 1, 1, 3, 2, and so on, right? These are what? These are, I mean, in a two-dimensional plane, these are the values of the features that you have, right? So for every data point you have these values, right? And these data points are distributed in a 2D space, and I would want to know whether there is this separating line, whether this line is good enough to separate the data points. Okay, a simple test would be what? Plug in this. So if I plug in 0, 1 here, what will happen is 0 plus 2 times 1. Idea is I have this. Now what is this? This is the line, right? Okay, so if a data point satisfies this equation, I can say that the point lies on the line. I mean, which is sort of not good news for us, because then we would not be able to assign it a class. That's fine. But if is this, then I can say that this particular data point lies above that line. On the contrary, if I have x plus 2y minus 4 less than 0, I can say that that particular data point lies below the line. And that way, we should be able to assign the data points to classes. Okay, so I can do a simple test. So let's plug in 0, 1 here. So if you plug in 0, 1 here, is 0 plus 2 times 1, 2 minus 4, that is minus 2. That is negative, right? So that means this point lies below the line, correct? Okay, so this point lies below the line. Okay, and if I plug in 1, 0, I meet the same fate. If I plug in 1, 1, it's the same fate. If I plug in 3, 2, it's on the other side, right? So all of these data points, they belong to class C2. However, this data point will be assigned to class C1. It's a simple test, right? So basically a two-class problem. We just want to see whether perceptron model, I mean, agrees with the general geometric discrimination kind of a thing. However, let me tell you at this point of time that perceptron, when it was first proposed, it was able to classify, it was able to solve the linear classification boundary type of problems. Okay, all right. And I'm going to show you an example where it could not actually solve a nonlinear decision boundary problem, and that's when it lost its popularity, went away, and came back in a new avatar. Okay, brought to by Hinton, LeCun, and those guys. I mean, the fathers of deep learning. Okay, when they proposed a neural network. Okay, where they did not consider just one neuron but a bunch of neurons. It's a much more complicated architecture. Okay, all right. So I mean, at least for now, let's see whether this guy is able to solve a simple linear problem, or at least how we are going to use perceptron to solve a decision boundary classification problem. So we consider a two-class problem. Okay, and we say that the class C1 has these data points minus 1, 1, minus 1, minus 1, minus 1, 1, and 1, minus 1, and C2 has 1, 1. Okay, and what I want to know is that which one below is a correct. Okay, this is by using a single neural model. And the options that I have are this. I have the following options: x1 minus x2 minus 0.5 equal to 0, minus x1 plus x2 minus 0.5 equal to 0. So what do I do? Simple, right? I mean, I have my data points. So let's say I pick something, right? I mean, I pick this guy. Okay. So, or yeah, whatever. So this is minus 1, 1. And so I pick these guys. So I mean, let's say we are able to fit this. So this is x1 minus x2 minus 0.5. So x1 and x2 are your input. So the coefficients of x1 and x2 are minus 1 and minus 1, and then there is 0.5, right? So this is your weight matrix, right? Correct? You are able to see that, right? This is the weight matrix, and the inputs we choose. So we can just take the first one, this one, right? So there is this input of minus 1, and let's say we have a bias term of 1. Okay. So clearly it's a single neuron model, right? So you have a perceptron over here, you have an S, right? It's a threshold activation. You have x1 and x2, you have x1 and x2, and then you have a bias term, right? All you want to know what is the output, right? Okay. Okay. And all you have to determine is that whether this output is positive, negative, or 0. That's it, right? Okay. So let's do this. So minus 1, 0.5, minus 1, 1, right? I mean, in fact, this should be written in a transpose fashion, right? So I multiply this. So I get 1, 1, 2 minus 0.5. So that is what? 1 plus 1.5, right? Okay. Did I do this correctly? Minus 1, yeah. So minus 1, 0.5, right? So this is positive 1.5. It's greater than 0, right? Okay. So it looks like if the C1 is here, I mean, at least it satisfies this line. I mean, so it lies above the line. Okay. So let's take the next one. So which is minus 1, 1, minus 1, minus 0.5, and this is the weight matrix, and then the data and the bias is minus 1, 1, and 1. Okay, so let's see what we get here. So this is minus 1 times minus 1 plus 1, minus 1 times 1 is minus 1, so 0, and then minus 0.5 to 1 is minus. So what happens is this is negative 0.5, negative. Okay, so clearly this is not working, right? I mean, because according to my observation, this minus 1, 1 point should be above the line, right? So not working. I don't think this is a good decision boundary, right? So in this way, what we can do, we can check each one of the decision boundaries. We can check which one fits. Okay, so this is how a perceptron model works. The next thing that we would like to see is where the perceptron model fails. And this is that famous XOR problem. Okay, all right. So just for quick recap, so a perceptron model is what? A single neuron, right? So this is simple input output model. So I have one neuron and I have a bunch of input data, and then there is bias. I take a linear combination. I just dump it to my threshold activation unit. It produces an output, and I just check the output with the target level. That's how it works, right? So between the input and the output layer, there is no other layer. Okay, so this is where the guys from Carradine, Hinton and LeCun, they came in and they said, look, I mean, this is not working. Okay, all right. So what we are going to do is that between the input and the output layers, we will have hidden layers. Okay, and then we'll have bias units passed on to the hidden layers, and we can have more than one hidden layer, and we can decide based on the problem that we are solving how many neurons we'll have in the hidden layer, how many neurons we'll have in the input layer, and how many neurons we have in the output layer. For example, for the MNIST problem, which is also due to Hinton, which is a digit recognition problem. So you have 0 to 9, 10 digits, right? So it's a 10 class problem. So the goal is to identify each digit with a reasonable accuracy. Okay, and the state of the art already gives you 100% accuracy. Okay, so that means that at least in the output layer you need to have 10 neurons, and each neuron storing one digit. Okay, all right, just for computation purpose. In the hidden layer you should have more neurons than the output layer, obviously. Okay, and the input layer is where you have to have the maximum number of neurons. And since it's a digit recognition problem, a standard 28 by 28 pixel image will have 784 neurons. Okay, so you'll have 784 neurons in the input, about 20 neurons in the hidden layer, maybe more than one hidden layer, and 10 neurons in the output layer. Okay, so this is how a neural net is designed. The first neural net was designed. Okay, but before I talk about that, let's introduce to you what is an XOR problem, and geometrically what kind of challenges it throws us. The XOR problem, we know the okay. Now, what will happen is, what we have seen so far is that the perceptron model is able to, you can use a single neuron model perceptron to, come up with a decision boundary, okay, which are linearly separable, which means the classes are perfectly discriminated on either side of the line. Okay, all right. However, if you think of this, if you try to visualize this problem, you'd see something like this, right? Here is your 0, 0. So when your inputs are 0 and 0, your output is here. That's 0. Okay, all right. And when your inputs are 1 and 1, which is somewhere over here, right? Okay, your outputs are 0. Okay, all right. So these two guys actually belong to so this is same class, correct? Because that's your class level 0. Okay, now you have 1, 0, which is over here, and 0, 1, which is over here. For both of this, your output class is 1, which is different. Now, so these are the distribution of your data points. Tell me, how are you going to, draw an axis, right? So basically, how are you going to draw a line which will separate, geometrically speaking, which will have these 2 points into one class and these 2 points into other class, right? So that's where the perceptron model failed. Okay, because what is happening is that you have a band which separates these 2 points from this. And there on the, there is no way, you can draw a line here, still no problem. You'll have a 50-50, it's like a coin toss, right? You can try, you can try infinitely many combinations of, a separating hyperplane, it is not going to work. Okay, all right. So therefore, what we do is we sort of build a basic neural network to solve this problem. Okay. And we know this, there are 2 inputs, x1 and x2, okay, and there is a hidden layer with 2 neurons, okay, and there is an output layer. So what is happening is I have the connections between each input, each neuron in the input layer. So this is my input layer, right, with the neurons in the hidden layer, right? Okay, so with some weights, okay, all right, and then there is a bias unit over here which has some weight, it's 30. that goes to one neuron in the hidden layer, and there is another bias unit, and this is something that you can afford in a neural network, right? There is another bias unit, okay, which is minus 10, okay, which goes to the other neuron in the hidden layer, okay. So what will happen is, I mean, the reason why we do this is because there are, different orientations. I mean, there could be positive values and negative values. So instead of using one standard bias, we just want to use two different biases. I mean, one is a positive bias and the other one is a negative bias. We hoping that the combination will help us overcome the geometric, hurdle that we face, okay. From the hidden layer to the output layer, we sort of have a uniform weight assigned to both neurons to the output, okay. So the idea is, between the input layer and the hidden layer, there is some function, right? There is an activation, okay. So you have a weighted combination of the input layer plus the bias. You feed it to the hidden layer. From the hidden layer, so what will happen here is that in this particular neuron, we will have an activation unit, which will be a combination of the input neurons, right? Correct? 20 times x1 plus 20 times x2, right? With a bias unit that is minus 10. Okay. What will happen here? Here we will have a minus 20 times x1 and a minus 20 times x2 plus 30. Okay. All right. Okay. Now, this is what you are going to get here. This will get squashed, right? And then when you travel from the hidden layer to the output layer, and when you generate the output here, what you are going to get is 20 H1 plus 20 H2, okay, all right, minus 30, okay. So that's the standard bias. All right. Okay. So far so good. Now we test whether this particular model is good enough, whether this neural network model is able to classify the problem. So what do we want to test? We want to test that given the inputs, let's say if we choose x1 equal to 0 and x2 equal to 0, whether the output level is 0. When x1 equal to 1 and x2 equal to 1, whether the output level is still 0. Okay. So the whole idea of neural network is, I mean, I really don't care how geometrically points are separated. As long as I can identify, I can predict the correct class levels without caring much about the geometric distribution, I should be fine. Okay. All right. So let's just look at this. Let's just take 0, 0 as the input. So what is happening from the input layer to H1? So you have O of H1, right? What is O of H1? O of H1 is nothing but 20 times x1, right? So 20 times x1. So this is 20 times 0 plus 20 times x2, isn't it? Which is 20 times 0, okay, minus 10, correct? Okay. So the number that you are generating here is a negative number, right? Okay, and we know we have decided that negative numbers correspond to 0 class level, and positive numbers will correspond to 1, right? Okay, so this is the output at the hidden layer with neuron 1. Now what about OH2? OH2 is nothing but minus 20 times 0 minus 20 times 0 plus 30. So what do you get? You get a positive number, correct? Because this is minus the 0, 0 plus 30. You get a positive number. Now this is the input. This is the input that you are going to use from hidden layer to output layer. So these are the values of your H1 and H2. Okay. Now, what is the function? What is the value that the function generates at the output layer? The function generates this, correct? So what you do is you compute this now. So you know that your H1 is 0 and H2 is 1, correct? So this is 20 times 0 plus 20 times 1 minus 30. So what you have is a threshold of minus 10, which is less than 0, which means this is 0. This is exactly what you wanted. Okay. So when the inputs are 0 and 0, the output is 0. Okay. So this is checked. Similarly, if I do this for 1 comma 1, and I'll just show this for 1 and 1. Okay. All right. So when I use 1 and 1, my OH1 and OH2 will be what? 20 times 1 plus 20 times 1 minus 10. So this is a positive number, right? So therefore this is 1. And then OH2 minus 20 times 1 minus 20 times 1 plus 30. This will be a negative number, so that will correspond to 0, right? So this will be my H1 and H2, 1 comma 0. So what will happen at the output? At the output, you are going to consider this, right? So here H1 is 1, so 20 times 1, H2 is 2, H2 is 0, so 20 times 0 minus 30. So once again, I have a sigma minus 10, which suits me just fine, right? And this will correspond to the 0 output. Checked. Okay. Just I'll take one example here just to show you that it does work for the other two. Okay. So here your H1 will be 20 times 0 plus 20 times 1 minus 10. So that will correspond to, that's a positive value, corresponds to 1. OH2 will be a minus 20 times 0 minus 20 times 1 plus 30. So what will happen is, this is negative, this is 0, this is negative, positive. So this will also correspond to 1. Okay. So your H1 and H2 are 1 and 1. Okay. So what do you expect here? You expect a 20 times 1 plus 20 times 1 minus 30. Okay. All right. So this is a positive number fed to the sigmoid. Therefore, the outcome is positive, implying that class level is 1. Okay. So you see how a neural network model, I mean a very, very basic neural network model is able to, classify this in the manner that you wanted. Okay. In fact, if I take the liberty of doing a little bit of improvisation, I mean, let's go back to this image, all right, and let's just look at this from a different perspective. So this is like, I think of this as a separating hyperplane, two separating hyperplanes as a matter of fact. It's a support vector, right? And I mean, if I tilt this, I mean, if I rotate this particular two support vectors so that they sort of, these are parallel, right? You see that these are parallel, correct? Okay. So these support vectors will actually project these 2 points 0, 1 and 1, 0 to a different plane, and by keeping these two in the same plane, you will have two different planes where each plane corresponding to a class, right? But if you tilt this, I am kind of going to get something like this, right? Somewhere down the line, I can perhaps think of using an activation like this. Okay, all right. And I mean, this is nothing but this. I mean, I can do this here as well, right? As long as the activation serves the purpose of projecting these 2 points, which are 0, 1 and 1, 0 to a different plane, I should be fine. Okay. So I have to now choose for an appropriate activation, but the shape of this activation function, I mean, sort of, is perfect given that these are the support vectors, right? This activation function is very familiar to us. I mean, it's used in logistic regression a lot, and this is sigmoid. Okay, all right, and we will see later, I mean, in a much more detailed explanation, that the functional form for this activation function is 1 over 1 plus e to the power minus x. So, instead of a non-threshold activation which we have been using so far, I mean, in the next series of discussions, we will be using a threshold kind of an activation, okay, and more solid concrete functional forms. We will discuss the limitations of the couple of activation functions, okay, and also provide certain situations where these problems can be remedied, okay. So I think that's about it for this session.